let's look at the theorems that pertain to the three C's of Dr. Cape Town: the center, the cyclic quadrilaterals, and chords that are equal. When we have an angle subtended by an arc at the center of the circle, that angle is double the size of the angle subtended by the same arc at the circle. So what that looks like in this instance is that that angle subtended at the circle center is going to be 2x, and that means that the other angle at the circumference that is subtended by the same arc has to be half the size, and in that instance is going to be x. Now note, there doesn't necessarily have to be an arc that's doing the subtending here. It could well also just be a chord that is here that is subtending both angles. You'll get exactly the same result. And the reason there is that the angle at the center is twice the size of an angle at the circumference. Now this particular theorem often creates confusion because it can actually appear in four shapes. Now, the first one we've already looked at, where you get this sort of, I want to say, a arrowhead. And then the next one is a wonky bow tie. So if we go look at the angle at the center, 2x, that is subtended by that arc, the angle at the circumference that's off to the side is also subtended by that arc, and so has to be half the size, and we call it x. Then we sometimes have this confusing image here where we have a diameter, but we can actually still use this theorem. So there, the angle at the center is 2x, and the angle at the circumference is actually subtended by the same arc, and so has to be x. And then when we've got this quadrilateral where we have 3 points on the circumference and 1 point at the center, we can use the major arc there that subtends that angle at the center that we call 2x, and then that same major arc at the circumference subtends the angle x. Then we can look at cyclic quadrilaterals. So angles subtended by a chord of the circle on the same side of the chord are equal. Right? So here, if you've got that angle that is subtended by the chord, and you've got that angle that is subtended by the chord, those angles are equal. And note, there doesn't have to be a chord, there can also be an arc, and the reason that we use for that is angles in the same segment. Now, you might be protesting at this point and saying, this is not a cyclic quadrilateral. It's actually a bow tie sort of thing, but it's definitely not a four-sided shape. Now, here, the reason I've put it under cyclic quadrilaterals is because we actually have 4 concyclic points in order to be able to use this theorem. So in the same way that with a cyclic quadrilateral, we're going to have those 4 vertices, the 4 points on the circle, in order to use this angles in the same segment formula or theorem, we are also going to have 4 points on the edges of the circle. And very often, we are going to apply this angles in the same segment when we do in fact have a cyclic quadrilateral where we have the diagonals drawn. Okay, so note also that the 2 angles that are in the same segment, and there I've highlighted the major segment, they have to be in the same segment. You can't have one angle on one side of the chord in the major segment and the other angle on the other side of the chord in the minor segment. Okay. So, this theorem actually gives us 2 sets of equal angles, because when we've got this bow tie, there's actually also the chord or the arc on the top of the bow tie that's going to subtend equal angles. So then, the angle that we've got there in green and the other angle in green, those are also angles in the same segment. So we actually get 2 sets of equal angles. We've got the orange ones and the green ones there. Now this theorem, as I did state, is very closely linked to the cyclic quadrilaterals, and it's because of the 4 concyclic points. Okay, so if I've got this bow tie here, and I actually just go join the points in that fashion there, then I do end up with the cyclic quadrilateral. And very often, as I did state, we'll end up using this theorem when we do have a cyclic quadrilateral with the diagonals drawn. Now here, a word of warning. make sure that you don't fall for the following pitfall. When we have that angle alpha and that angle theta that are both subtended by the same chord, those two angles are not equal because of angles in the same segment, and that is because all 4 points must be concyclic. They must be on the circumference of the circle, and that angle alpha there is not at the circumference of the circle. So don't make this mistake of saying that alpha and theta are equal to each other. Now next up, if a line segment joining 2 points subtends equal angles at 2 points on the same side of the line segment, the 4 points are concyclic. Now here, it's very much a case of, in the past, when we had the chord and the 4 concyclic points, then the angles are equal. Now, if we have the chord and the equal angles, then the 4 points are concyclic. So again, it's the same pieces of the puzzle with just a different part that's missing. So here, if that angle x and that angle x are both subtended by the same chord, then we can claim that the 4 points are concyclic. They would fall on the same circle. And our reason for that is that the line subtends equal angles. Now, again, that chord doesn't actually have to be there. So even if we have this bow tie here without the chord, there's an implied chord there that still is going to be subtending those two equal angles, and so we can still claim that we do have a concyclic, 4 concyclic points that fall on the same circle, and there again is your cyclic quadrilateral. Now here, tip, use what you prove. Now, because of these two angles in the same segments that were equal, we claimed that the 4 points are concyclic, which means that what we do have in orange there is, in fact, a cyclic quadrilateral. So if in a particular question you've proven that you do have a cyclic quadrilateral, think about what that means for your riders. Are there other theorems or other bits of information that you can now find using that knowledge that you do in fact have a cyclic quadrilateral in your rider? Okay, let's keep going. So the opposite angles of a cyclic quadrilateral are supplementary. So if you have that angle x and that angle y, they have to add up to 180. P plus Q has to add up to 180. And your reason is opposite angles of cyclic quadrilateral. If the opposite angles of a cyclic quadrilateral, not quite. If the opposite angles of a quadrilateral are supplementary, in other words, they add up to 180 degrees, then the quadrilateral is going to be cyclic. So here, given that x plus y is equal to 180 degrees, we can then claim that actually the 4 points are concyclic. In other words, that quadrilateral is a cyclic quadrilateral, and our reason is opposite angles quad sup. So basically that just means the opposite angles of a quadrilateral are supplementary, and therefore it's a cyclic quadrilateral. Okay, so then what else do we know? We know that the exterior angle of a cyclic quadrilateral is equal to the opposite interior angle. So if we have that angle x there, that has to be equal to the opposite exterior angle, and the opposite exterior angle Q has to be equal to the opposite interior angle, which we can then also call Q, and we call that opposite angles of cyclic quad. Now here, just a common pitfall, the external angle has to be formed by extending one of the sides of the cyclic quadrilateral. So here we can see that this has been drawn by extending the side of the cyclic quadrilateral, and then you get this external angle here. If you, for example, have something like this, and let's say like this, we can see that these two lines are not an extension of one of the sides of the cyclic quadrilateral. So this here is not an external angle of the cyclic quadrilateral. We can't claim that it's equal to the opposite interior angle. So then the converse is also true. If the exterior angle of a quadrilateral is equal to the opposite interior angle of that same quadrilateral, then the quadrilateral is cyclic. So if we know that that angle is x and that external angle is x, then we know that the quadrilateral is cyclic, and our reason is going to be the external angle is equal to the opposite interior angle. Then, if we have chords that are equal, we know that equal chords subtend equal angles at the circumference of the circle. So in this particular triangle there, we can see that we've got a chord that subtends an angle, and in that particular triangle, we also see we've got a chord that subtends an angle, and we were told that those two chords that are now highlighted in yellow, that they were actually equal in length. And as a result, the two angles that they subtend also has to be equal in length. And our reason is going to be that when we have equal chords, we have equal angles. Now note that these angles don't even need to be at the circumference of the circle. If we have angles at the center of the circle and we have equal chords that subtend that angle or those angles at the center of the circle, then we get exactly the same result, that those angles at the center of the circle are equal. And then in very, very rare cases, you might even have identical circles with equal chords in those circles, and then those would also be equal, but that's not something you're going to see very often. So let's have a look at an exercise here. In the following, E is the center of the semicircle. ABCD is a cyclic quadrilateral. BAC is 30 degrees, that's given, and then ACD is 25 degrees. The questions are to find the size of DBC and to prove that triangle EBC is equilateral. Remember, an equilateral triangle is one where all of the angles and all of the sides are equal. And in that case, all of the angles have to be 60 degrees. Okay, so let's see here. I'm going to start, as I always do, with Dr. Cape Town. So I'm going to find the diameter. Now, because it's a semicircle, that means that AB is a diameter, and that then means that ACB has to be a 90-degree angle that is subtended by that diameter, and the same goes for D, that is also a 90-degree angle that is subtended by the diameter. Then I'm going to move on to the R, and whenever I have radii, I am going to mark them as being equal. Now, because I've got those three equal radii, I actually see that triangle AEC is an isosceles triangle. So this is where I'm using my VIP tips. The I is for isosceles triangle. So I know then that that angle opposite the other equal side is going to be 30 degrees. And then I also now have a triangle in which I've got two of the angles, so I can go find the third, and then 180 minus 30 tells us that AEC has to be a 120-degree angle. But then we can see that AEB is a straight line, and angles on a straight line have to add up to 180 degrees. So now I know that that angle CEB is in fact equal to 60 degrees. And again, we have an isosceles triangle. So we know that the base angles of that triangle, EBC, have to be equal. But because that angle CEB is 60 degrees, the other two angles have to add up to 120 degrees. And because those angles have to add up to 120 degrees and they're equal, then 120 divided by 2 is 60. So that then means that ECB is 60 degrees and that B there is 60 degrees. And we've actually then already answered the second question. We've shown that ECB is equilateral, and that's because all of the interior angles have exactly the same size. Then we can start using our angles in the same segment. So we can see that AD subtends B as well as subtending C. So because that ACD is 25 degrees, we also know that ABD is 25 degrees. Then we can do the same thing where we actually just take the 60 degrees and we subtract the 25 degrees from it in order to get 35 degrees. And that's going to give us then DBC. Then angles in the same segment again. DC subtends DBC, and DC also subtends DAC, and so we know that A is 35 degrees. And then we can again use angles in the same segment because CB subtends CAB, and CB also subtends CDE and CDB, and so those angles are both 30 degrees. So we found the angle that we were trying to find. We've proven that we've got an equilateral triangle, and that is again a fantastic application of Dr. Kepler.